a stream in Kafka as a topic, right? So there's an input topic of documents, there's an output topic of counts by word, which is updating as new things arrive. And so this allows you to build a program which reacts to change in the world, right? You can build a program which subscribes to things happening in your company and reacts and updates itself. And it can either update its local state, which is kept with the application, or it can publish out that result, which can be loaded into some additional system. And so that doesn't seem too hard to do, right? You could just subscribe and do that with the Kafka consumer. But what this really enables is it actually allows you to scale this out, right? And so this simple Java application, this is actually a complete distributed system, like in a box, right? If you start one of these, it will subscribe to all the documents, and it'll do all the counts in that one instance. But if you start another one on another machine, now you've actually scaled it out over two. And half the data will go to that one, and half the words will be maintained, and half the counts will be kept in the state of that second application. You start a third, and it will be divided up into threes. If one of those fails, the results will be moved back over. The state, the counts that are being kept, is actually fault tolerant. So as that, as one of those machines dies, that state will be reinstantiated on the remaining nodes. So it's quite sophisticated, despite being just a simple library. And that simplicity is really the goal we were aiming for. And so I'll highlight three areas that I think this makes building streaming applications simpler, right? And you can think about this as being either simpler than one of these like full-fledged stream processing frameworks, or simpler than just building against a messaging system style API. And so the three areas I'm going to dive into is how this uses Kafka, how it operates really without a central cluster you have to deploy into and manage. And then finally, how it allows you to process tables of data, which is super fascinating, I think. So the first simplification is just about how this is integrated with Kafka. So one of the nice things about this is if you understand Kafka, you basically understand kind of most of what you need to know to do distributed stream processing. It inherits the same data model as Kafka, kind of key value pairs with a timestamp. It uses offsets to control what has and has not been processed, just as Kafka does. It relies on Kafka for the kind of back pressure within your processing flow. It uses the same partitioning mechanism to divide up data that is being processed. It uses the same group management mechanism to scale out and determine who's alive. So in a sense, these stream processors are just kind of a natural part of Kafka itself. It also allows you to reprocess data. So one of the key problems in stream processing is if you update your code, you want to be able to kind of go back and reprocess data. And it allows you to do this by just kind of rewinding in Kafka and replaying that stream through your processing job. And it integrates a notion of time based on the timestamp that's integrated into Kafka. So if you're counting the number of events that happen in a 1 minute period, and events come in late, they'll update the window of the day where a part of an event occurred. This is called event time, which is really important for getting correct results. So that was the first example, was really just being a natural part of Kafka, relying on everything that's in Kafka for security to fault tolerance and failover. The second aspect of this is, not needing any kind of additional cluster. So, a Streams app, an application built using the Streams API, it's just an application, right? It's doing the processing just in your application process. The processing isn't happening in the Kafka cluster or anything like that. And it scales out just like a Kafka consumer would. So if you started 2 instances of your app and they connect to Kafka, they would split up the data stream. If you start a third one, it will take over a fair share of the processing dynamically. You don't have to go back and reconfigure anything. If one of these instances dies, that will be detected, and the other 2 will take over. And so, effectively, what's happening is, we're not forcing you to create a cluster, but we are giving you that kind of elasticity that you might expect for your application that uses this. What we don't do is we don't actually take over the problem of how you that's intentional. I actually think it's not the right thing for a framework which wants to enable distributed processing to try and get into the business of orchestrating processes and deploying processes. And the reason for that is there's really kind of a lot of mechanisms for deploying processes, right? And there's a lot of development in this area, and you will see people have already adopted mechanisms. And some people would label the left-hand side very cool, the right-hand side very cool, and the left-hand side very uncool. Some people would probably say very reliable and very unreliable. It doesn't matter. The key point is you have a mechanism for managing applications. You don't need another mechanism which is bolted onto the stream processing framework. And you definitely don't want one of these mechanisms bolted onto every type of system you use because it becomes so involved in your life. And so the key point with the streams apps is they can be deployed in any of these mechanisms. So if you're using Puppet or Chef or Ansible or whatever it is to deploy applications, you can deploy your streams app that way. It's just a Java application. If you want to put it in Docker, you can use Docker. If you want to get the Docker containers out there in Kubernetes, you can absolutely do that. That's basically orthogonal to the problem we are solving. What the problem we are solving is if you have an application, can we get the data? Can we manage fault tolerance and the semantics around distributing that data over the instances of the app, right? And I think that's exactly the right division of labor. You don't want your stream processing framework doing anything but stream processing, right? So this is how we divided up the problem. I think this is very important. The final aspect of what we've done that I think is extremely powerful is making it possible to combine streams of events with tables of data. And this is one that probably takes the most effort to grok what on earth I might be talking about. But let me give an example that I think kind of helps make it a little bit more clear. So I showed this example. I said there was some kind of, at least at the business level, there was some type of stream processing happening here, right? I'm not claiming that most retail stores implement themselves with stream processing, although Walmart did a fantastic job on how they rebuilt a lot of their stuff around Kafka and with stream processing, so it is absolutely the case that people are doing this. So I said this is really a lot of stream processing, but it's actually not just streams here, right? So you have events or streams of things that are happening. A sale is something that happens, a shipment is something that happens, but you're also maintaining something else in response to that. So you're maintaining something like inventory. How many products do I have on hand? And that's not exactly a stream. It's more like my current state, right? And so if I have a sale that occurs, I guess my number on hand goes down. If I have a shipment of new products, probably my number on hand for a bunch of products goes up. And I'm maintaining that in reaction to these events. And so you can see in this example, I'm combining a kind of table of my current state with streams of things that are happening. And I can't really do it without having both of those concepts. If I have just one concept, I don't really solve the problem. And so the question is, how can you integrate this into streaming? How can you provide an API which allows you to do both of these things? And to answer that, let me kind of step back and say, well, what's a stream? Well, we said it's kind of like a log, right? It's a sequence of key-value pairs. That's going to be, in Kafka, the representation of a stream. Well, what's a table? I think everybody knows the answer to that. A table is some kind of rectangular thing with rows and columns, right? In this case, let's say we have two columns, the key and the value, and we could shove a lot of things in the value column if we wanted to. I think everybody agrees that's a table. But the question is, if you have a table, it's not really just this, right? Because you change it. And so unlike a log, which I was just appending to at the end, a table is kind of getting poked and mutated all the time. And so if I have a table, it's actually not so much that picture. It's more like this picture, where at one time it looked like the first thing, and then the next time it looked like the next thing, and then maybe it evolved more, right? So in the first case, I had one entry, and then I maybe inserted key 2, value 2, and then maybe I updated key 1. And you have the sequence of evolutions of your table, right? If you took a backup of your database every time you changed something, these would be the dumps of your database. So maybe this is more like what a table really is as it evolves over time. It's like a sequence of tables. But it's a little bit inefficient to back up your database every time you change it. So what you actually end up doing, in reality, with a database is if you want to get continuous something which is equivalent to this sequence of tables, which is the sequence of updates, right? And this sequence of updates is actually a pretty powerful representation of that table, right? It's what was being modified in the table. Why is it powerful? Well, it's powerful because it doesn't just tell me the table at one point in time. It tells me the table at every point in time, over time, right? And it's something which allows me to update as the table evolves. So how would you represent that as a string? Well, it's just the same way, right? You just take those puts, which were key value pair updates, and you arrange them in a stream. And so you can think of a stream which represents updates as being a representation of the table. It's kind of a weird idea, right? But in this streams API, we actually give that a pretty high-level representation. We say, hey, you can subscribe to a topic which maybe is coming out of a database and represents updates to a table. And you can actually treat that like a table. You can join it onto streams of events. So you may have a stream which is activity by your customers. You may want to join on information about the customer, attributes about the customer. You might want to compute something off of that, maybe aggregate it or so on. Being able to represent both of those concepts is really important. And so these tables allow you to do joins or aggregates like sum, count, that kind of thing. And they allow you to bridge this gap between streams and tables. So here's an example many people have maybe heard of. It's kind of a common problem in a large company that you have lots of bits of information about your customers spread over a bunch of applications or a bunch of databases. And so one project every company does is try and stitch it back together, right? Try and get a complete picture of the customer across all the different customer service activity and the account information and the billing people and clickstream data, just get that all together into one thing, maybe for marketing purposes, maybe for many purposes, right? So you can actually think about that as a stream processing problem. You have a number of databases, you're taking a stream of changes and you're materializing a kind of view of your customer which updates every time any of these sources update. And you can imagine doing this in streams, and you can imagine combining that with other activity records as you need to in a stream processing system. And it turns out that this works in the other direction as well. So I talked about doing processing on tables which are being represented as streams. But it turns out that when you compute some kind of count, right? So let's say that I'm counting the number of clicks from my customers per minute. That count is actually also being updated as it evolves, as new clicks evolve. And that can also be represented as a table. And so, the Streams API uses this table concept not only as representing input, but also representing output, representing things that you derive. And so let me talk a little bit about what this enables. So I claimed that somehow Streams was going to make this complicated architecture for stream processing get simpler. And indeed it does, right? So we're able to kill off the stream processing framework and just run the app directly. We're able to maintain local state and kill off that side database. We're also able to kill off the batch processing side of it as well, because we can do reprocessing off the Kafka feed. And we can get down to an architecture that looks more like this. But we even have an opportunity to go further, because in the newer version of Streams, we allow you to directly serve requests against the application you built. So maybe you're computing the count of actions your user has taken, and you're doing that as a stream processor against the feed. You can also make requests to find out what the current number of actions that have been taken is. So you can even collapse this last bit if you choose. Now, there's many reasons you might want to have an external database if that goes to, but you have the flexibility of doing either. All right, so that was a little bit about the Streams API. How do you get these streams? Where do you get data for stream processing? This is kind of the other of the newer APIs we've added to Kafka. We've added an API called Connect, which allows you to build connectors that kind of suck in streams of data from data sources or publish out continuous streams to sinks. And this of course works in conjunction with streams, and then you can suck in data that comes from databases, you can transform it with streams, you can publish that to some other destination. You can think of it almost like a kind of streaming ETL, where the extract, the E, and the L, the load, would be connectors Streams app, which is computing something off the stream. And like Streams, Connect kind of tries to do the hard work for you, so it tries to make it possible to scale out these connectors, to manage them centrally, capturing schema information, making them fault tolerant. And they absolutely work together in a picture kind of like this, where you can have some Streams app, which is doing transformation on data that comes out of this. And I talked a little bit about how that's kind of like streaming ETL, although often in a real-time manner and often in a more operational context, not just feeding a data warehouse. And this kind of feeds into this streaming platform vision that we have, where you can capture streams of data that come out of operational systems, out of applications. You can do processing on these streams. You can feed real-time analytics off of this. You can feed data warehouses or Hadoop clusters off of it. And you can use Kafka as this kind of unifying message bus across those. And I'll mention just super briefly what we're doing at Confluent. So we kind of started this vision at LinkedIn. We built Kafka and the source it there. We've really been, since left LinkedIn and founded the company Confluent, we've been working on Kafka there, doing a ton of work to advance this vision. Also producing something called Confluent Platform, which is a distribution of Kafka. And for that, we're really just trying to put together all the pieces we think people need to get going. We have an open source version of it, which is just tools for REST access and clients for Kafka in different languages, and some of these connectors that people use to connect up to common systems. And we also have an enterprise offering that adds multi-data center capabilities, allows you to balance data within your Kafka clusters to spread the load dynamically, and allows you to have this application called Control Center, which kind of manages and monitors the Kafka center. So that's kind of what we've been doing at Confluent to try and make this whole streaming platform vision something that's like relatively easy to get going with without spinning up a software development team to build out all the tooling and integration. And that's it. If you're interested in this area, I guess there's a fantastic Kafka meetups you can attend in your area. There's also an upcoming Kafka Summit in New York, which is happening in May. We have a super active blog at Confluent. We publish all kinds of articles on the streaming areas, so you can follow along there. And I'm super happy to take any questions that people have on the Streams API, on Kafka, on Confluent, on future roadmap plans, technical questions, anything that's on your mind. Question?
You mentioned you already worked on that Samza.
Yeah.
Can you elaborate how Samza compares to Kafka Streams? Is it more a lightweight version, or is it feature-wise or wise different? Or?
Yeah. I mean, so we originally thought about doing Streams, kind of in the Samza project as a continuation. But we felt actually there was a fairly large amount of big changes to make. So it ended up being more like a successor system, if that makes sense. So the differences between Samza and the Streams API and Kafka are a few. So Samza is kind of built on Yarn, which is a Hadoop framework for running programs. There's been some attempts to decouple it and make it work with different frameworks, but it's relatively difficult to do that in the model it has. Samza also provides a relatively low-level API in that we basically give you a message and your application kind of responds to that message in some way. Streams does have that lower-level API, but it actually gives you that kind of nice DSL on top, which allows you to do things in kind of a declarative manner, where you kind of say map, filter, join, aggregate. So that's another difference. This whole concept of tables is something that was done in the Streams API. There's kind of some notion of maintaining statements, but I think it's significantly more sophisticated with the Streams API. And then finally, the Streams apps actually model a complete data flow. So not just one transformation on your data, but a sequence of them. It's not necessarily clear because that DSL is so concise. But under the hood, this is actually sending data potentially between the instances of the app, performing in-memory transformations on it, and so on. So those are kind of the areas that we wanted to take, an additional step, in addition to just being able to rely on Kafka for things like security security and the group management feature for fault tolerance versus relying on yarn for
So if you're starting to rebuild with this and you have to, and you're looking at Samza and Kafka streams, that's with the reason Kafka streams, there's actually no reason at all to look at Samza. Or
yeah, that's my opinion. I think in terms of features, the Streams API is probably at parity or significantly ahead. There's definitely still people at LinkedIn working on it. Sometimes it's an open source project, so these things go on and on. And I think those people are adding things and probably innovating in their own way, so there's something bad with it. But I think if I were starting something and it was going to be using data from Kafka, I think no compelling reason not to use the built-in Streams API.
yeah, does it also mean that Samza will eventually, slow down because everyone will start using Kafka streams?
That's certainly possible. I mean, I guess I think these open source projects have a whole community around them, and so as long as people like it or are running it, then they'll keep liking it and running it. I guess I would say certainly for new things, I would probably adopt this. Any other questions?
What is the next coolest feature coming to Kafka?
There's a ton going on, so that could be a talk in its own right. One thing that's really exciting, I think that's a bit technical, is we're working on improving the semantics of Kafka in a way that helps Kafka, helps the connect library, goes all the way through the streams. And so, with Kafka or really any messaging system, you have problems around the delivery of messages. So Kafka obviously persists the message, replicates it, guarantees that it's not lost, right? But you can have duplicates in Kafka. If you publish a message to Kafka and you kind of lose your network connection, you don't know if that message is written, you can kind of retry, but if you retry, you may deliver it twice, right? This problem is exacerbated if you're doing stream processing, because imagine I'm counting messages. If I have a duplicate, I don't have a duplicate count, I actually have a wrong count. And so, coming up, not in the next release, which is happening in about a month, but probably the one after that, we're doing a set of features around providing what people typically call exactly once semantics, which enable you to, get around that problem. It's really a couple different features. One feature which makes the writes into Kafka idempotent, and it does this in